the easiest way to try to relate normalization. And I thought the normalization integral that I put here is probably the most simplistic way of doing it. And Landon, you're the math guy. Make sense?
Yes.
I mean, I got this formula from somewhere, obviously. I didn't make it up.
Given the probabilities of over all space and time, you sum up all the probabilities for something that exists, you'll get 1.
Yeah. So I saw this formula. I thought this was the
universe
easiest way to
3.
describe it. Yeah. Unlike some that positing supernatural probabilities out there, you know who you are. They don't exist. There's no such thing. You have to have. It has to be 1 to 0. So, anyway, that's your range.
Yeah.
Okay. Next. Now we get into some fun stuff. Like I said, there will be math involved. It's not that complicated. This is like high school stuff. So, basically, how does this all relate to this question? The distance formula in two-dimensional Euclidean space is basically derived from the Pythagorean theorem. We all learned this: a squared plus b equals b squared plus c squared. Now, you can kind of manipulate that formula, and you kind of get d is equal to the square root of the square of the distance between two points on the x-axis plus the distance between 2 points on the y-axis, or the difference, I should say. So I could basically make a vector here, and a vector is basically a direction with a magnitude. So how far you want to go and what direction. That's a vector.
SQR means square root in this case.
Yeah, SQR is square root. I didn't want to do a square root symbol, so I used the actual SQR. But for 3D space, you can actually transform it a little bit, and you could do it with z-axis. So as you guys know, on a two-dimensional Cartesian plane, you have x and y, but in three-dimensional space, you got x, y, and z. So this is the distance formula. So if I want to figure out what's the distance between two positions in space, this is what I would use: non-Euclidean. Euclidean. So this is not for a non-Euclidean space, because obviously, as Landon pointed out, with Euclidean space, you have curvature, and so you have to take that into account, because you're not going to have a straight line in free space. You're going to have a curve. All spaces. There's no such thing as two parallel lines in non-Euclidean space, because they eventually curve at some point. Okay. Next slide. I don't think we need to kind of go into that at all, unless you guys have anything to add to that.
No.
Very basic. All right. This is where it gets interesting, and this is, I think, one of the cruxes of why using the no boundary proposal uses very advanced techniques, but it's not really explaining what happens before the Big Bang, or maybe even what happens at t equals 0. How this works with the Hawking state is it uses what's called imaginary time. So normally for a four-dimensional manifold, you add in time, so you have the d squared equals x squared plus y squared plus z squared minus t squared. Okay, so that's how you would relate distance in space-time. So d squared is some interval in space-time, but that uses real time, and that's incompatible with general relativity at t equals 0, because we already established at t equals 0, general relativity doesn't work. So what they try to do is they rewrite t squared using just a little bit of math, where I is equal to the square root of -1. You guys remember? I'm talking about the audience, by the way, not you three, the audience. He's one of the best mathematicians in the world. He's explaining imaginary numbers to him. Okay, but basically, to the audience, I is equal to the square root of -1. It's kind of a misnomer. People always tell me they really hate the fact they call it imaginary numbers, because they exist in the same way real numbers exist, but they're just on a different plane. And so, or a different field. Is it a different field or a different? It's a different field, they call it, right? I get field and ring mixed up. Landon, I would complex field.
Yes.
Okay. I'm gonna call it the complex plane. That's simpler. So
it's okay to say complex plane. We do.
Yeah, I'm going to say complex plane, because that's the way I remember learning it mostly. Like if you have a Riemann sphere, that's going to be on the complex plane, and so you have a complex infinity at the North Pole of the Riemann sphere. So I kind of related it to a plane, right? These fields and rings and groups and all that ring theory stuff that gets way more complicated than I'll ever hope to understand. But what it does is it basically just takes the formula and puts it positive. So you have t squared, which is a positive value, which doesn't break down to t equals 0, but you're using imaginary time to do this, right? So what does that mean to have imaginary time? Do we actually exist in imaginary time? Well, I don't know. That's where I have to like say, well, is it really modeling reality if it's dealing with imaginary stuff? Somewhat. I mean, complex numbers do model reality in sense of rotation, I guess. But I mean, how do you guys look at this when you're dealing with imaginary times to relate to t equals 0? And I am going to ask Athena on this only for the fact like she did a very specific video on no boundary condition. How do you kind of like look at the way that Hawking took the no boundary proposal and said, okay, I'm going to use imaginary time to kind of get to the base of the shuttlecock, they call it, the shape that the inflation period made after it came out from that initial t equals 0.
Yeah, so looking at it as imaginary time is trying to make a parallel mirror to what a time is here. So rather than being on a complex plane, when it comes to, obviously, I'm using imaginary numbers, trying to, obviously, like saying that there is actual existence, saying that there is, as if everything is still constant as it is now, it would be just as constant as it is there. And that's the whole purpose, is to try and create a parallel understanding of what we have now, and then try to just repeat that, but by using, I guess imaginary time as you're saying, because it's going to be t equals, trying to reach t equals 0, where the equation can actually withstand, and general relativity will not completely fall apart. So it is trying to make it in a sense where like things are exactly as they are now. Physics is still withstanding as it is now, and just looking at it from just a different using imaginary numbers. So exactly what you said is it's not that we're trying to say that like, no, we don't exist, none of this is actually in existence, because the whole purpose is to try and find a way that it'll work in this realm, so in this complex plane, and then try and make it as replicable to today, like I guess real standards, so real time standards, as opposed to imaginary time. So all the variables are supposed to be directly relevant to our universe as it is today. So that's from my understanding of the no boundary proposal and what Hawking was working on. That is the sole purpose. So as far as you asking about whether or not this was supposed to be, the same conditions in which we are in today, it is supposed to be withstanding in both realms, if we can say. I guess that might be a relatively okay term to use right now, because it's all the same variables. You're just using imaginary time. So yeah.
There you go. Okay, that exactly the way I look at it. Dr. Kroon, you want to touch on that?
Well, the only thing I'd say is, so Steve, this is getting into a topic that you like a lot, which is like philosophy and, epistemology and stuff. Like, is it real or not? Well, of course, it's non-real in the sense that the term we use is imaginary, but is it reflected in reality in a real quote sense? I don't know. I like I said before, I'm a scientific.
It kind of dives into more philosophy at that point, right?
Yeah, they're definitely useful for solving differential equations, and they show up a lot in solving circuit problems and quantum mechanics. It's all over the place. So I don't know. They're definitely useful, and so I guess by my existence and my usage of them, they have a little bit of realness to them in that sense, in that instrumentalist sense.
In the instrumentalist sense, sure. Landon?
Yeah.
I mean, don't confuse the model with reality.
Right.
This is a good model for describing reality. Whether reality works this way or not is perhaps irrelevant to the value of the model, which is helping you describe what you're observing reality.
Mm-hmm.
Okay. Next slide. Okay, so what does this all mean? So in order to even try to express what happens at t equals 0, even understand any of this, you got to know a hell of a lot of shit. Let's be honest. This is not easy stuff. To even approach the question, what happens before the Big Bang? Yeah, it's nothing that you're going to dive right into without having some kind of basic understanding of a lot of different complex topics. It's combining mathematics, it's combining cosmogony, it's combining physics, it's combining mathematics. A whole bunch of different subjects are required to even start to approach something of this magnitude. It requires very complex normalization techniques, and they are very complicated. Dr. Kroon can attest to that, I'm sure. The use of imaginary time, and to even attempt to describe what happens at t equals 0. So my overall point of this is to kind of give everybody, whoever wants to look into this, these are the things that you kind of need to look into if you're going to really understand Hawking's no boundary proposal and what it means to even ask the question, what happened before the Big Bang, because there is literally no real time at t equals 0. So there cannot be anything before t equals 0. So to ask the question, to me, it's still nonsensical because you're dealing with now imaginary time to even get it at t0. Now, Landon had brought up things like the big bounce, and the multiverse, which kind of gets into things like meta time and other things, but they're not what we're talking about as far as time in our universe. So I'm going to maintain that while it's productive to ask the question, what happened before the Big Bang, it's still a nonsensical question. Again, if I asked you, point to me on the real number line where the imaginary number is one, where I exist, it's nonsensical. But is it a productive question, maybe from a pedagogical approach, by saying, hey, look, it's not on that line. I'm showing you that's not on there. So is there educational value out of it? Sure. But it doesn't make sense to really attempt to legitimately ask that question when it's a nonsensical question. That's my summation. I think is that my last slide? Dave? Okay, one next one. And then you guys can do your summations. It doesn't get you to before the Big Bang. It cannot be used to describe conditions at t less than 0 because there is no space, there's no time, imaginary and otherwise, to measure. There's just, I'm going to say nothing now. It gets into philosophy whether there's nothing before the Big Bang, because again, there's just a nonsensical statement there. So I don't even want to say there's nothing before the Big Bang. I think the whole statement is nonsensical. But Stephen Hawking's attempt to describe t equals 0, what we know now as the no boundary proposal, simply does not get you to anything, quote, unquote, before the Big Bang. And also, I did want to note this. It assumes Lorentzian over Minkowski space, which I think is a big thing. Now, that's just my view from reading into this. I'm really just pulling that out of my particular interpretation of this, that we don't use a Lorentzian or neo-Lorentzian model. You do use a Minkowski space model. So it takes a very different approach to how we look at space-time and how we look at spatial dimensions with relationship to emergent temporal dimensions. But I think now this one's the last slide, right? Dave, is that the last one?
No.
And then you guys can wrap up. How many more I got? Oh, okay. I remember now. I was like, wait a minute.
This one and two more, Steve.
These are quotes? Okay, so let's just rush through this because we're running out of time, and then you guys give your summations. In Stephen Hawking's own words, events before the Big Bang are simply not defined because there's no way one can measure what happened at them. Since events before the Big Bang have no observational consequences, one may as well cut them out of the theory and say that time began at the Big Bang rather than anything before the Big Bang. So that's in his own words. Next one. He also wrote in A Brief History of Time, as we can see, the concept of time has no meaning before the beginning of the universe. And one could still imagine that God created the universe at the instant of the Big Bang or even afterwards in such a way as to make it look as though there had been a Big Bang. But it would be meaningless to suppose that it had been created before the Big Bang. And I think Landon kind of touched on this, and it does get into more theology and philosophy. If some entity exists out space-time, how did he create something in time? It makes no sense. To say that there was a time before the universe such that something existed and that created all this, it's a very difficult. I don't think it makes much sense for a non-temporal entity to make something that's temporal. But that's my position on it. But we can get into quantum foam. We can get into how the bubble expanded, and you kind of did a little bit earlier, but that's not a being doing that. It's not a non-temporal being doing that. So next. And the end. So the question of what happened before the Big Bang is nonsensical. That's my summation. So let's kind of get your guys' view on this. Let's wrap it up. I don't want to keep it too much longer. Athena, I'm going to save you for last, if I may. because you're new, and I'm going to give you the longest thing that you need to do to wrap up and make sure that people do subscribe to you. So I'm going to actually start with my co-host first, Landon. What do you got to say about the presentation?